Maybe. Hi, everyone. We have Dr. Ilias Mavromatis from Columbia University today. He's a postdoctoral research scientist in the Stochastic Engineering Dynamics Laboratory at Columbia University. He earned his PhD in civil engineering and engineering mechanics from Columbia after completing a diploma in naval architecture and marine engineering at the National Technical University of Athens. His research has primarily focused on developing path integration techniques originating from theoretical physics to determine the response and assess the reliability of complex stochastic dynamic systems subjected to diverse excitations such as wind, earthquake, and sea waves. More broadly, his research lies at the intersection of applied mathematics, computer science, and engineering, with ongoing efforts to incorporate quantum computing tools to tackle computationally challenging engineering problems. He has authored 5 peer-reviewed publications and received recognition, including Columbia's Middling Scholar Award and the ASCE EMI Best Student Paper Prize. Ilias, you can take over from here. Thank
Awesome.
you.
Okay. Thank you very much. Thank you very much for the introduction, and thank you very much for inviting me. So today I'm going to talk a bit about my research on eigenvalue analysis of stochastic structural systems, a quantum computing approach. This is a joint work in collaboration with Leonidas Paliadouros, a PhD student in our group, and Professor Ioannis Kouliantzou. So, get right into it. I'm going to begin with some introductory remarks about challenges in stochastic dynamics and in general engineering mechanics. And of course, I'm going to discuss a bit about the current state-of-the-art techniques that are used to address them. Then we are going to proceed with quantum computing, which is the main topic of this presentation. I'm going to talk a bit about how it came to be, describe some fundamental aspects, and talk about the current state of quantum computing. After this, we're going to continue with the main problem that we are trying to address. That is the eigenvalue problem in stochastic structural dynamics. I'm going to talk about the computational cost challenges associated with this problem and introduce finally a quantum computing framework to address this problem. Last, I'm going to show some numerical results and leave some time to discuss. So in engineering dynamics, in general, we deal this problem of this form. Here we have a second-order nonlinear oscillator, where here we have the mass, damping, and stiffness matrices, and G is a nonlinear function that can depend on the state, but also on time. W here is the external forcing. So in general, what we like to do when we analyze and design such systems is determine the response. And of course, regardless of the application platform, this comes with several challenges that we have to face. First, I would like to mention the complexity of the modeling itself. With advancements in physics, data processing and collection techniques, as well as in general, an incentive for financial and environmental efficiency, our models are becoming more and more complex, and thus our systems are becoming harder and harder to solve. Another challenge that I would like to mention is stochasticity, which is assumed throughout my work in general. This is what I deal with every day, as well as this presentation. And stochasticity can come into play in 2 ways. First of all, we might have stochasticity in the excitation. You can imagine that we would like to design a building that operates in windy conditions, or we would like to evaluate, let's say, the survival probability of a building under an earthquake. But stochasticity can also come into play with the system parameters themselves. In that case, you can think of anisotropic materials that are described by finite element models. And of course, we can have a combination of the two. Today, the most prevalent challenge is, however, the high dimensionality of the problems that we're trying to solve. And we would like to have techniques that are accurate, versatile, and as I'm going to address a bit more today, computationally efficient. In the field of stochastic dynamics, the most prevalent solution scheme is Monte Carlo simulation. Basically, we take this equation and we solve it a number of times for realizations of the underlying stochastic process. After doing so, we can conduct statistics and get the solution, as we say, to our system. Other techniques include statistical linearization, stochastic averaging, and so on. In general, traditional techniques can be divided into two groups. One group has techniques that can address lower dimensional systems, but do so very accurately. And the other group includes techniques that can address high dimensional systems. However, they provide lower order statistics, maybe in the form of mean and standard deviation. So what all modern techniques aim to do is push this boundary over here and become the best of both worlds. Among these techniques is also linear path integral techniques, which, as Oske briefly mentioned earlier, has been part of my research as well. So if you would like to truly revolutionize the field and move into a new direction, is basically we can do that by tapping into the potential of quantum computing. And this is what we're going to talk a bit about next. Let's begin with some historical remarks. Quantum computing as an idea first came up in 1981 by Richard Feynman when he asked the question if there is a probabilistic computer that can simulate quantum mechanics. Feynman, along with other pioneers in the field, such as David Deutsch, came up with the idea of constructing a quantum computer that is fundamentally based on the principles of quantum mechanics. One big breakthrough came a few years later with the development of the quantum Fourier transform algorithm by Coppersmith and Shor. Shor specifically found a very interesting application that is the factorization of very large number. This has great implications today in cryptography. And the truly interesting thing about this algorithm is that for the first time it was proven that it can perform its task much faster than whatever it is possible over a classical, compared to a classical computer. This is what we usually refer to as quantum supremacy. Another big development came a year later with the quantum phase estimation algorithm by Kitaev. This algorithm can determine the eigenvalue of a unitary matrix. And the interesting thing about this algorithm is that its computational cost does not depend on the size of the involved matrix. In fact, it only depends on the accuracy we would like to achieve, which in turn depends on how many times we have to evaluate some powers of this matrix. Regardless, quantum computing has been a quite interesting subject. And over the last few years, industrial partners have shown great interest and have actually been the driving force behind major developments, especially as far as the engineering, the actual physical quantum computer is concerned. In that regard, IBM has built a processor with a lot of qubits. Google has proposed another quantum processor that has fewer qubits, but includes error correction, which is a challenge I'm going to discuss briefly later on. And Intel proposed another architecture about a processor that can scale up fairly well into the future. I should also mention that Microsoft have also proposed their own way of thinking and constructing a quantum computer. However, there's been some controversy regarding the validity of their claims, specifically if what they said is already achieved, is actually achieved, and if it's just a theoretical result. So I haven't included that in this slide. Regardless, quantum computing over the last few years has shown excellent potential in cryptography, chemistry, finance. But the field that I would like to address and I'm involved with is, of course, engineering and specifically stochastic structural dynamics. So let's talk a bit about how quantum computing works. So in classical computing, the fundamental unit of information, the way we represent our information is binary. The bit takes two forms, that is either 0 or 1. Conversely, in quantum computing, the fundamental unit of information is the qubit. The qubit is defined in this way, where 0 and 1 here are called our basis states, and alpha beta are some complex numbers that tell us that a qubit is a linear combination of these basis states. Usually we say that the qubit is in superposition of its two base states, and that means that for a single qubit, it can take any value within this sphere. So as you can imagine, this is the property that allows qubits to represent vast amounts of information much more efficiently than classical computers. Another property that is fundamental to quantum computing is that of entanglement. Entangled qubits are correlated in such a manner that the state of a qubit cannot be defined independently from the state from the rest of the qubits that it is entangled with. And that is basically the property that gives quantum computing the ability to conduct computations much faster and, in a sense, in a parallel manner. So how do we actually conduct computations in quantum computing? So similarly, with classical computing, we conduct computations by using gates. Gates such as these are used to alter the state of the qubit to create superposition, entanglement, and in general, carry out any operation we would like to. Here we see some examples of single qubit gates that might flip the probability amplitude to these numbers here, or might change, for example, the sign as you see here. I forgot to mention earlier that alpha and beta are called the probability amplitudes, and their modulus, since we're talking about complex number or just their square magnitudes, if we simplify it into real numbers, give us the probability that the qubit on measurement will collapse into one of its two base states. So when we measure it, we have alpha squared probability that will measure this qubit as 0, and conversely beta squared to measure it as 1. So applying these qubits, we can conduct operations, and of course, this can be generalized also for multiple qubits. In practice, what we do is we bounce a few gates in something that we call a layer, and we use many layers to conduct operations. These many layers form what we call a quantum circuit, and its size, how many gates are involved in it, are quite important in the efficiency and feasibility of the algorithm, especially today. And I will explain a bit more about this later on. So considering superposition and entanglement, quantum computers can exponentially represent more information when compared to classical computers, and also can conduct computations very fast in a parallel way of sorts. So the thing that comes into mind now is why don't we have a quantum computer today? And of course, there are several challenges why we don't have a computer today like that. First, I'm going to mention a bit about the hardware limitations. First of all, creating a qubit that is of good quality remains its state, it's quite difficult. And as you can imagine, qubit is a quantum mechanical object, and that means it's affected by its properties, such as quantum fluctuations, and its state is quite volatile and can change very fast. Another major issue involved in quantum computing is that of noise. Quantum computers are affected by environmental noise quite a bit, which can lead to changing their states or interacting with our operations in any sorts of ways, and that can actually cause errors. To provide a very brief example, you can imagine building a physical quantum computer in a lab. That lab is bombarded constantly by cosmic rays. Any interaction of one of these rays with a qubit might alter the state, and it's very hard to predict that, detect that, and correct for that. So these errors come up quite often, and what we would like to do, similar to classical computing, is detect them and correct them. In classical computing, this is usually done by error detection and redundancy techniques. However, in quantum computing, more sophisticated methods are necessary since errors are more complex in nature. In fact, this is due to many reasons. But first of all, inspection of a qubit makes it collapse into one of its deterministic based states. This makes it lose all of the advantageous properties that we wanted to conduct fast operations. Another factor is that we cannot actually copy information in a quantum computer. That is because of the no-cloning theorem. Therefore, things are quite more complicated. So what we would like to have are techniques that are able to detect errors, but without directly interacting with them, and at the same time correct for errors without needing to copy information. So as you can imagine, these techniques get very complicated. And of course, if we want to build a big quantum computer that can actually address real-life, large-scale applications, then all of these challenges are magnified even more. On the other end of things, some other limitations relate to the theory and algorithmic development. We need, of course, algorithms that are faster compared to classical computers, so we can have an actual justification to use a quantum computer, but we also need to identify problems that can actually be implemented in those computers. One big criticism that quantum computers face today is that quantum supremacy has more or less only been proven in problems that are irrelevant for practical applications. Therefore, we need to find ways to reformulate our problems into such a way that we can actually implement any quantum computing approach. And another challenge that it's useful to mention is standardization. As I described a bit earlier on during my introduction, each industrial partner has its own processor, its own architecture, and in general, its own way of writing and doing things. This is an extra layer of complexity than when that a new user has to circumvent or mitigate when they get into quantum computing. And of course, that means also that the development in general happens quite independently of one another. So it's quite a slow process. This brings us to the current state of quantum computing. Today, we are in the noisy intermediate scale quantum era, or NISQ for short. Today we have quantum processors that have anything from 50 to 1,000 qubits. I should mention, however, that not all of these qubits are used in computations. We cannot take full advantage of them. Some of them have to be reserved, let's say, for quantum error correction. But also not all of these qubits can be interconnected and tagged with one another. That is because this process is quite complicated, it is quite susceptible to noise, and therefore we do not really tap into the full theoretical potential of qubits and quantum computing. Of course, as I described earlier, we are significantly affected by noise. It's very hard, as I said, to predict, to detect all sources of noise, predict for them, and actually correct for them. And error rates are too high to claim that we have a fault-tolerant computer yet, quantum computer. So what can we do today? Today, by far the most useful approach and the most widespread approach is to use what we call variational quantum algorithms, or VQA for short. These algorithms are hybrid in nature. They combine the efficiency of a quantum computer with the versatility of classical computers. They do that by offloading part of their computations on quantum computers. These are quite suitable for today's devices because they're quite robust to noise. That's due to the classical computer's ability basically to treat noisy situations pretty well. But they also require shallow depth circuits, meaning that we don't need a lot of gates, which in turn means that we don't need a lot of qubits to implement them. So they don't have as many requirements in terms of resources that we have to use. So how do these algorithms work? Is basically we have a problem. We reformulate this problem based on a variational principle and define a cost function with some parameters theta. And then we follow an optimization procedure to optimize for these parameters until convergence to a suitable solution is achieved. All of this bridges basically the gap between having a classical computer that works perfectly today with a fully fault-tolerant quantum computer. Here we can see a schematic of a variational quantum algorithm, and I'm going to briefly go over its parts so we can understand a bit more how they operate. First of all, we need to define a reference state. This can be regarded as the initialization of the algorithm. For example, you can say initialization is all zeros. Then we need to define the parameterized quantum circuit. This is basically the variational form of our problem. It's a bunch of layers of gates that describe the search space of the algorithm. This is described basically the space in which our solution lies upon. Then we need to define the cost function. This is the objective of our problem that has to be minimized or equivalently maximized. All of these, along with some initial parameters for the cost function, are fed into a quantum computer, which evaluates the cost function, and then we measure that result, plug it into a classical computer, and we optimize. We actually have a new prediction, a new estimate for the parameters theta that is fed back into the quantum computer. This process, of course, is followed and until we reach some optimal solutions. And here's exactly where you can see the hybrid nature of the algorithm. Of course, implementing VQAs can be quite hard. First of all, it's quite sensitive to the choice of hyperparameters. The reference state and parameterized quantum circuit have to be chosen it's actually, I should say that the VQA is quite sensitive to the choice of the reference state and the parameters. And in general, it has been shown to be an NP-hard problem. Therefore, ideally, we would like to have techniques that allows us to choose the initialization in such a way that we can at least make more likely convergence to an optimal solution. Another challenge that is also common in classical computing, let's say in machine learning, is the optimizer tuning. As in any optimization technique, we have to choose the right technique, the right step size, the right number of iterations to ensure that the algorithm is efficient and also accurate. And finally, probably the most important result is the search space design, here as I described a bit earlier. This and such in general, this combination of these two parameters has to be balanced in terms of expressivity, meaning that our circuit must be designed in such a way that it includes actually the solution to the problem we're trying to solve, but must also be relatively shallow. It must require quantum resources that are actually feasible today. So as you can see, it's a bit of a balancing act between those two things. And this balancing act can be quite challenging. So let's move on a bit to the main problems we're trying to address. Here we have an n degree of freedom undamped system. And of course, we can reformulate that into deterministic eigenvalue problems. Solving these kinds of problems is crucial to understand the system behavior. For example, the natural frequencies can help design, let's say, vibration mitigation strategies to avoid resonance in systems. Alternatively, you can see that we can use these frequencies to exploit response amplification techniques when we're trying to design, let's say, energy harvesters. Of course, solving this problem has a computational cost in classical computing that scales with the cube of the dimensionality of the problem. And this, as you can imagine, for very large finite element models, let's say, this can become prohibitive quite fast. Next, if we also count for uncertainties, if these parameters, the involved matrices kappa and m are random, then this limitation becomes even more obvious. To solve such a problem, the most common approach is to resort to a Monte Carlo simulation technique. And for n realizations, the cost scales even faster and can explode and become quickly prohibitive. So what is usually done today is a resort to classical semi-analytical or even analytical approaches, as you can see here, to determine a subset, usually not all the eigenvector eigenvalue pairs. I'm going to briefly talk about the matrix iteration technique later, but also other techniques exist that can address such problems, usually for the deterministic case, but they can be done also in a Monte Carlo simulation framework. This problem has also been addressed using a quantum computing approach. Ilias and Kano were the first, I believe, to do so. Their technique for the deterministic problem relied upon the quantum phase estimation algorithm to determine the smallest only eigenvalue, the smallest natural frequency. However, they achieved a quite low success rate, around 50%. This is because to implement, I should say, the quantum phase estimation algorithm, you need to have at least an estimate for the associated eigenvector, and their approximation was quite crude, which led to a lower success rate. Other efforts include those by Liu and Sato, which relied upon variational quantum algorithms to, again, estimate for a deterministic problem, the smallest eigenvalue. So what we're going to propose is another quantum computing approach. First of all, let's see how the eigenvalue problem is formulated in quantum computing. Here we have H, the Hermitian matrix for which we would like to evaluate the natural frequency, the eigenvalue, with its associated eigenvector psi. By far, for this kind of problem, the most prevalent technique used in quantum computing is the variational quantum eigensolver. This algorithm has shown great potential in quantum chemistry, as well as condensed matter physics. This algorithm is based on the Rayleigh-Ritz variational principles, which you might have heard of. Basically, the eigenvector that is associated with the eigenvalue for which we are trying to determine can be approximated by a set of orthogonal functions, and then we can evaluate that eigenvalue by minimizing this expectation function. In quantum computer, this basically means that we need to build a parameterized quantum circuit that approximates the trial eigenvector. And of course, as I said earlier, this must be general enough to include the solution, but also compact enough to make it feasible in current existing NISQ hardware. Doing so, our cost function takes this form, which I'm not going to get into for reasons of time. And what I would like to mention is that the main limitation, perhaps the only limitation of this technique, is that it computes only the ground state, which means the lowest eigenvalue of the system, which is useful, but it's not usually enough if we want to conduct proper analysis and design for a structural system. So our approach relies on these two extensions of the VQE, the previous algorithm that I was talking about, the subspace-search VQE and the variational quantum deflation algorithm. The first one basically takes advantage that the eigenvectors of a matrix are orthogonal with respect to each other. So it approximates all of them together using a basis of orthogonal functions. And doing so, it can evaluate any numbers of eigenvalues you want, perhaps all of them, in one optimization. VQD works in a different way. First of all, it uses the VQE to evaluate the smallest eigenvalue and then enforce orthogonality. Basically, it takes advantage of the fact that, again, one eigenvector is orthogonal to all the previous ones. So it applies a penalty term that says that the next eigenvalue for which we're trying to determine is orthogonal to the previous one, and it repeats this process a number of times until we evaluate all the eigenvalues we want. I should mention that both of these algorithms require more resources when compared to the VQE that I referred to earlier. However, they also give us more eigenvalues compared to the VQE. To be more specific, the VQD algorithm requires the same amount of qubits as the VQE. However, it requires circuits with larger depths. which might make it more challenging to implement in current hardware. On the other hand, SVQE requires more complex strategies, which might make it more susceptible to errors. Also, it can be argued that the SVQE is more efficient since it just performs one optimization, whereas the VQD needs to do it repeatedly to evaluate the eigenvalues. In practice, as far as the performance of both algorithms in terms of accuracy is concerned, it has been shown that the performance is dependent both on the type of the problem we're trying to address as well as the scale, but we will see and compare both next on the eigenvalue problem. So, what makes the eigenvalue problem suitable for a quantum computing approach? So the advantage the eigenvalue problem has that makes it suitable is that some of the limitations associated with utilizing variational quantum algorithms, and in particular the ones I described earlier, these challenges can be largely mitigated. First of all, regarding hyperparameter calibration, which is, as I mentioned, an NP-hard problem, what we propose is to start by classical matrix iteration estimate for the smallest eigenvalue. Then we can use that estimate to, in a sense, calibrate the parameters of the unsage and the reference state. And that can basically ensure faster convergence and actually fewer resources when compared to other techniques. Another thing that we should mention is concerns the cost function evaluation. The matrix H, which takes this form in the eigenvalue problem, and for which we want to evaluate the eigenvalues, needs to be represented in a quantum computer in a way that it is understood. This basically means that when we want to actually implement it in a quantum computer, we have to decompose it into a number of gates. Usually these are Pauli gates. However, the matrices involved in engineering and structural dynamics are often sparse and symmetric, and therefore, as we'll see later on, they admit more efficient decomposition, and the resources scale linearly with degrees of freedom, which makes these kind of example quite promising for quantum computing implementations. Finally, when we actually want to address the random eigenvalue problem, all of this can be done, all of the tuning can be done only once. We suggest that we find and tune the unsage and the algorithm based on the mean values of the parameters involved, and reuse these parameters across all Monte Carlo samples. This will save a lot of time when we have to actually implement the variation quantum algorithm in an actual quantum computer. But to move on with some examples, here we have a chain-like structural system with these mass and stiffness matrices. We choose our mass to be deterministic, as you can see here, but our stiffness matrix is stochastic. Theta here are independently distributed variables with zero mean and unit standard deviation. And epsilon here is a magnitude scale that gives the scale of the stochasticity and is chosen in such a way that we don't ever get negative stiffness. Considering this problem, we have this associated random eigenvalue problem that we would like to solve. Following the quantum computing implementation that I previously described, here first we need to design the circuit by also choosing a number of gates that will have to be used in the algorithm. We initialize the circuit, and then we choose the classical optimization scheme as well to carry out the optimization procedure. And all of these choices affect both the degree of accuracy as well as the feasibility that I talked a bit earlier on. For the initialization, what we propose is that we use the matrix iteration technique to evaluate a crude, I should say, excuse me, estimate for the smallest eigenvalue. The smallest eigenvalue, exactly to be exact, corresponding only to the mean values of the mass and stiffness matrices. Doing so, we can use, as I said, these estimates to calibrate our ansatz. And after we do so, we can use these parameters in a Monte Carlo simulation framework and conduct statistics to determine the mean and standard deviation. In fact, this was done for the first time in engineering. For the first time ever, we implemented and carried out Monte Carlo simulation for a random eigenvalue problem on an actual quantum computer. In particular, we used IBM Sherbrooke, which is a quantum computer which has a processor with 127 qubits involved in it. And as you can see here, these are the mean values of the eigenvalues we would like to estimate for a 2-degree of freedom system. And as you can see, when compared to classical results, I'm fairly good agreement. Here in the left, I also have the results from a quantum simulator. You can think of that as a software that tries to simulate the actual quantum computer. These are usually used because there's a limited amount of quantum computers, and there's even more limited access to them in terms of time and actual resources you can use. So they're often used as a benchmark and as a proof of concept result. And as I mentioned earlier, a big thing that we have to keep in mind is feasibility. And here we see that the matrix we use with increasing degrees of freedom, the Pauli gates that are required for its decomposition scale linearly. This shows that basically our resources demands do not explode, and this kind of problem seems to be a very good candidate to implement the quantum computing approach that we developed. And here you basically see the same results but for a slightly bigger system. This is a 4-degree of freedom chain-like system of the same structure we described. And here we performed again Monte Carlo simulation, and we evaluated both the mean and the standard deviation. And as you can quickly check, the results are in quite good agreement with the classical ones. It's useful to mention here that for the SSVQE, I've only included the results for the first 3 eigenvalues. This was due to the fact that for the SSVQE, the depth of the circuit that we needed to build was actually unrealistically large. Therefore, to stay reasonable and actually applicable to today, we chose to show only 3 out of the 4 eigenvalues. Another numerical example that I will go very briefly over is this symmetric circular matrix. This is a similar structure as we saw before. We have a deterministic mass matrix on the one end and the stochastic stiffness matrix on the other end. And systems with cyclic symmetry can be, for example, braided disks, propellers, and so on. And for these kinds of systems, there have been developed various analytical even solution treatments, including for the analytical determination of the exact eigenvalues. However, we chose this example because we would like to assess, as I said earlier, the performance of quantum computing in cases where the involved matrices exhibit symmetries that are quite common, but are also quite useful. And as you can see here, we've shown that for this example, with increasing degrees of freedom, the resources, at least in terms of Pauli gates, scale sublinearly. And here we see also the implementation. Here we compare against exact values because we actually have a closed form solution. But it's another good indication that our approach can be very useful and reasonable to be implemented even today in quantum computing frameworks. So to conclude, today we have developed a quantum computing approach based on the SSVQE and VQD algorithms that can evaluate the eigenvalues of a stochastic structural systems using a Monte Carlo simulation approach. Why we chose that problem is because first of all, we can evaluate all eigenvalues, which is of course critical when we want to analyze and design structural systems. These kind of systems include matrices that often exhibit the properties of symmetry and sparsity in such a way that enable a compact Pauli gate composition. this is, as I said earlier, again, very critical for implementation in quantum computing. And of course, we have addressed the big challenge of hyperparametric initialization based on a classical approximation using a very standard technique. And as far as results are concerned, we have shown the first ever Monte Carlo implementation of the eigenvalue problem on a real quantum computer, as well as some proof of concept results regarding the accuracy on a simulator. And we saw that the accuracy, when compared to classical results from Python, lie within a few percent for the examples we have shown. So thank you for your time, and open to any questions you may have.
Thank you so much, Ilias. It was a great
Well, I
talk.
cannot hear you, Oscar. Not sure.
Are there any questions from the audience?
I still cannot hear you. I'm not sure why.
Oh,
Mm,
can you hear me?
I'm not sure why I cannot hear you. I'm not
I
sure if it's only
can
me,
hear
maybe,
you.
perhaps.
I don't know why you aren't able to hear each other.
Oh, but can you hear me, Valerie?
I can hear you.
I
Yes,
cannot,
I
I'm sorry,
can.
but I cannot hear you. This is,
Oh no.
oh, how can we?
Okay,
Can
I'll try
anyone
to
else hear
type in
you?
the.
I'm not sure.
Maybe people can put their questions in the chat.
Yeah.
Oh,
I'll
sure. Okay.
just.
I can see the questions in the chat.
Okay. I'll read it out loud, and hopefully Elias will respond. My first question is, how do you approach learning new fields like quantum computing that are outside of your original training?
Oh yeah, yeah. With regard to high approach learning new fields. First of all, I came into quantum computing when I learned about a paper that was trying to do path integration. This is the first part. So I tried to see if I can implement it directly into the research that I was trying to work on. So the first step was, okay, how we actually use it? Like what the correlation between the two? And then it was quite obvious that it was much more complicated than I initially thought, but that basically sparked the interest. Luckily, in Colombia, quantum computing is being regarded as a quite important subject for the future. So I just audited a class here and started getting into more about quantum computing, but it took a lot of time. This is a result basically of 2 years of me getting into it, and this is also quite a preliminary result, and we aim to push a lot forward. But what I would suggest in general, it's just find find a hook from your research that you're currently working on. See if that is applicable in quantum computer, and since you understand the fundamentals of your problem, then you can slightly work slowly backwards and actually get familiar with the concepts and the tools and trying to do your own thing and implement it. Regarding someone's question, where does the speed up over classical methods come from? Uh, uh, Basically, the speed up comes from the evaluation of the cost function that I described. As I said before, using a hybrid algorithm, you basically evaluate the cost function onto a quantum computer. In classical computing, in general, doing things like matrix multiplication is by far the most costly thing, and this can be done basically in one step using a quantum computer. That's where basically the speed up comes from. Can classical Monte Carlo methods be used for this problem? Yeah, you can use classical Monte Carlo methods, of course, but again, the cost there scales by the cube of the dimensionality of the system, whereas basically the cost in a quantum computing framework is transformed into an optimization problem. So the speed up is quite immediate. Have you considered an extension to quantum Monte Carlo? Yeah, I have considered actually that there have been methods developed for quantum Monte Carlo, usually mostly about random walks. It's quite difficult to implement in an actual quantum computer. There have been some theoretical results, but it's still further far on. But yeah, I've consumed extension to quantum Monte Carlo, and it's something that I'm working on currently. So it can be achieved, but there is some work to be done first. Okay, regarding the most challenging part of your work, by far the most challenging is getting familiar with the quantum computing. But after you get familiar with that, the right terminology, the right tools, then it becomes obvious that quantum computing is very new. So there's no standardization. So you read papers, you see demos or whatever, and even words that one person uses are not the same with the words that another person uses. So it can be quite obscure. So you need to read a lot. You need to understand the fundamentals very well to get into it, which can be quite time consuming.
Hi, Ilias. Thanks a lot for your talkings.
I'm not sure
And-
why, but I cannot hear you. Maybe if I am sharing. This, I'm sure if
Can you
what
hear
advice
now?
would I give for younger researchers? Uh, I say that first of all, I would say to pursue interdisciplinary research opportunities because having a wider actually viewpoint can help you in a lot of ways to be inspired and to do new stuff and keeps things interesting, at least in my opinion. But I would say that start slow, start from the fundamentals. Keep in mind that even though you have experience in a very complex field that's quite developed, when you're trying to switch into something very new, such as quantum computing, things are quite slow. So be patient, pursue it, and communicate with people that are experts in the field. We have a department in Colombia, for example, that have professors that do quantum computing, and we have relied on their opinion and for direction quite a bit throughout this process.
Are there any other questions? I think Yang Rong was saying something earlier.
Okay, so regarding theta and how many parameters you need and the dimensions of theta, basically that is defined by the problem itself. As I said earlier, you begin with a problem, you use a variational principle to translate that into a cost function, and that cost function is basically what defines the dimensionality of theta. But what I said earlier, you need to balance a bit how many of these parameters you use to create the right search space. These parameters basically define your quantum circuit. This quantum circuit needs to be expressive enough. You need to actually be able to evaluate your solution, but at the same time, you need to be able to actually implement it. So the dimensionality, it's a bit of a balancing act. You cannot really, even if you actually, there are some theoretical results that you can determine a priori how many of them you need. But in practice, you need to balance that in order to actually be achievable in current computers. Yes, the initial guess of theta influences the estimation quite a bit. That's why we proposed this sort of calibration technique. Basically, we get a crude estimate using one or two iterations of a very simple, very well-known classical scheme from the 60s or even before that. And we just do analytical evaluations. And we use that to find the right set of parameters that converts to that solution. Thank you. Thank you for your questions. It's very interesting. It's very nice to discuss these things.
If there are no other questions, I would like to thank
Thank you very
Ilias
much, Jessica.
again.
Thank you very much again for inviting me.
Yeah, of course. And don't forget to follow him and his research. And we will be back with more seminars next month. Thank you.